Hi, good evening, Professor Naresh.
Hi, Vidya.
Hi, how are you?
Good, thanks.
Good. Okay. Yeah, I think some of the participants are still having class.
All right, okay.
Yeah, so we're still waiting.
Yeah, we are coming to the end of the year very soon.
Yeah, and in the next 2 weeks, you will be having Christmas.
Yeah, so we close on, the university closes on the 21st.
Okay, 21st. I thought that it will be
and
this week.
Open on 3rd of January, so it's,
Oh, yeah.
yeah.
Yes.
Hello, Naresh. Hello. How are you?
Hi, good, thanks.
Okay. Nice to meet you again.
Yeah.
Mhm.
Sorry, Shalihan, how are you?
Yes.
Good. Good to see you.
Okay. Happy New Year.
Oh, yeah, that's right. It's not very far.
Yes.
Yeah, only we are closing on 21st, like I was saying.
Okay. Oh, yes. Long
So
weekend.
tomorrow, Tuesday is our last day.
Mhm.
And then on Friday, we have school Christmas party.
Oh, yeah.
Yeah. So time flies.
Yep.
Yeah.
Are you going to somewhere, Naresh?
Sorry?
Are you going to somewhere for New Year?
Oh, actually just thinking of going to maybe Newcastle.
Newcastle.
Yeah. Or go to South Coast, Wollongong.
Wollongong.
Yeah, but cannot fly very far because the situation is not very good.
Yes, okay. Yes.
And now this new virus, Omicron, is causing problems. We have like 500 cases almost every day now.
Okay.
Okay, thank you, Naresh. Yeah, thank you very much for
Okay,
your
all the
lecturing.
best. So we will hopefully see each other face to face one day.
Yes.
Yeah.
Yeah, actually, I'm missing Sydney.
Right. Yes. Yeah, Sydney is a good place to be in.
Yeah, it is. And good place also for studying.
We got a new light rail now, which goes from the
Yeah.
university. Yeah.
Yeah, the moment I went back, I went for good. I couldn't see the light rail because it's still under construction. So,
Yeah. But now it's already.
Right. We have around 70, 60, yeah, around 65 students. Okay. Yeah, I think, shall we start now? Professor Naresh, okay. Right. Thank you. Good afternoon, everyone. Thank you for joining in the Visiting Professor Lecture Series on Organic Chemistry. And today is actually our last meeting with Professor Naresh. It's the 10th meeting, and Professor Naresh already gave us a lecture since October, right? Yeah, since October, and now we come to an end, and yeah, time does fly so fast. And in today's lecture, Professor Naresh will continue explaining about alkyne, and for all students or participants, if you have any questions, please, for today, do not hesitate to write your questions in the chat, or you can discuss with Professor Naresh, because yeah, sadly we come to an end, and I hope that that all of us can use this opportunity wisely. And I would like also to say thank you to Pak Solihin, Prof. Asep, Ibu Gebi, Ibu Amelinda yang sudah hadir dan bergabung di kelas sore ini. Dan yeah, I think time is yours, Professor Naresh, please.
Okay, all right, let me share my screen so that it works. Got it. Yeah, I think you can see my screen now. I just make it full. Just give me 1 second. All right, and I just get a pen. All right, thanks for the introduction again, Vidya. It's been really a big pleasure for me talking to your students, and hopefully trying to teach them a few things. I hope they learn something from me, but we will continue with the final topic today, and then towards the end we can have a more general chat. They can ask me questions about the subject, but they can also ask me questions about University of New South Wales. If they want to come to Sydney in future, they can ask me anything. Okay, I think I introduced the topic of alkynes already in the last lecture. So alkynes are basically hydrocarbons. Hydrocarbon means that they have only carbon and hydrogen in them, and these contain a carbon-carbon triple bond. And carbon-carbon triple bond is a very special bond. And we saw in the earlier lectures the reactivity of the alkenes, where we had a carbon-carbon double bond. And today we're going to talk about carbon-carbon triple bond and their reactivity. The reactions we're going to look at are going to be very similar to the reactions of alkenes. But obviously, because the triple bond is present, you will find the reaction can take a funny course. And maybe some of the reactions can happen twice, because the triple bond is there. It might go to double bond first, and then it might go to single bond after that. So we're going to be looking at that. And that's just a model structure showing the triple bond present at the end and the triple bond present in the middle. And compounds with triple bond, they have a Y and E at their name. So instead of alkenes, they had E and E. Triple bonds, they have Y and E at the end. It's ine. Okay, and we also learned about nomenclature very briefly in the last lecture as well. And alkynes are named as substituted acetylenes. What do we mean by that? So these are some of the examples we looked at in the last lecture. You look at the longest carbon chain that is present, and then you try to give the carbon where the triple bond is the minimum numbering possible. For example, in case of ethine, which is 2-carbon chain, it doesn't matter which end you start from, it's still going to be 1 ethine. So that's why we don't really give the numbering here, because it's understood that there's only one position where the triple bond can start from. But when you got a 4-carbon compound, like coming from butane, so the compound becomes butane. But here, the carbon where the triple bond starts is given the minimum numbering. That's why it is called as 1-butane, because the other possibility is that you can have a situation where you can have a carbon, triple bond carbon, and another carbon. This is also a butane, right? That's 4-carbon chain. And in this case, the numbering will be 1, 2, 3, 4. So this will become like a 2-butane rather than 1-butane. So here you have to define the number where the triple bond starts. Otherwise, there's a confusion which butane we are talking about. And the same thing applies to if you have more than 4. If it's 5, then it's pentyne. And again, you try to give the carbon with the triple bond the minimum numbering, so that becomes 2-pentyne. And also, if you got a substituted long molecule, don't get too worried. What you need to see is what is the longest carbon chain that is present in this molecule. And that is a 6-carbon chain that is present in this molecule. And then you need to see where the triple bond is starting, which carbon has the triple bond. So that's the 2 position has the triple bond. So it becomes a 2-hexyne. So draw out the name of the parent compound first, the longest carbon chain compound first, and then see where the substituent is. So this one at the 4 position has a methyl group. So we call that 4-methyl-2-hexyne. So that means it's a 6-carbon chain alkyne with a methyl present at the 2 position. So one of the questions which students sometimes ask is that if we have a double bond and a triple bond present in the same molecule, how do we assign the name of that compound? So if you can see this structure here, it has a double bond, which is shown over here. There is a double bond. And it has a triple bond, which is shown over here. So the question arises, should I name it according to an alkene, or should I name it according to an alkyne? So if that is the situation where you have a triple bond and a double bond, in terms of assigning the ene end is given a lower number. So in this case, the alkene carbon is given the lower number. So if you look at this here, this is 1, 2, 3, 4, 5, 6. The double bond is starting at the 2 position, and the triple bond is starting at the 4 position. The other way could have been if we put 1 over here, 2 over here, and 3 over here, and 4 over here, and 5 over here, and 6 over here. Then the compound could have a lower alkyne number, but that's not correct. What we want to do is to give the double bond the lowest number. Okay, so the double bond starts at the 2nd carbon. So this compound is 2-hexene. Ene stands for the double bond. And the triple bond starts at the 4 position, so that becomes 4-ine. So this compound will be named 2-hexane 4-ine, not the other way around, where we are saying is 2-ine, and the hexane is present at the 4 position. So if you go double and triple bond, in terms of numbering, the double bond takes priority over the triple bond. And another example is here. This is also an example of a hexyne. And you can see that numbering starts from the alkene end, where the double bond is, not on this side, because if you start from this side, then the numbering will be different, and it would not be a correct. That's 4, that's 5, and that's 6. So that means the nomenclature has to be where the alkene has the lowest number, starts at 1 carbon, the double bond. So it's 1 hexene, and the triple bond starts the 5 position, so that becomes 5-ene. Not the other way around, where we have 5 hexene and 1 ine. So something to remember if you have a double bond and a triple bond present in the same molecule. In the last lecture, we sort of finished off here that the carbon-carbon triple bond has got a planar structure. If you look at acetylene, you can see that all 4 atoms, the carbon and the hydrogen, they are present in the same plane. They are like flat. They're like in the same plane. And the angle here is 180 degrees. So just like the straight line. Often many students make a mistake when they're writing triple bond compounds. They write it as like this. They put a hydrogen here and they put a hydrogen over here. This structure is incorrect because the 4 hydrogens have to, the 2 hydrogens have to be in the same line as the carbon, because the angle here is 180 degrees, because this is an sp carbon, and sp carbon has that 180 degrees angle present in that. So this will be an incorrect structure if you draw it like that. And if you look at the structure of acetylene, there is a carbon-carbon single bond, carbon-carbon sigma bond, and then there is 2 pi bonds formed as well. And then the carbon is forming a sigma bond with the hydrogen and a sigma bond with the hydrogen. And the sigma bond is formed by the sp-sp overlap, and then the p orbitals form the 2 extra bonds, the pi bonds, which are present to give you that acetylene structure or the triple bond structure. So this blue here represents 1 pair of orbital, and this one here represents another pair of orbital. And these are the 2 double bonds that are present. 2 double bonds in addition to the sigma bond that is present in acetylene. So they are electron-rich compounds, and a lot of their reactions are gonna be based on that. And just to summarize again, that the triple bond is composed of a sigma bond and 2 pi bonds. So there is the carbon-carbon sigma bond in the middle, and then you got 2 pi bonds, which form that carbon-carbon triple bond. Okay, now let's look at some of the reactions which we saw in the case of alkenes also apply to the carbon-carbon triple bond. So what we're looking at here is electrophilic addition of hydrogen halide to alkynes. We're gonna look at HCl, but this reaction is equally applicable to HBr if you got HBr instead of HCl, or if you got hydroiodic acid, HI, you will get very similar products in this case. So the addition is a bit like the carbon-carbon double bond, the alkene additions we saw. The carbon-carbon triple bond is a electron-rich system, just like alkenes, this electron-rich. And HCl, the hydrogen here, is an electrophile, because we know HCl can be split into H plus and Cl minus, okay, because it's an acid, and H plus is your electrophile. So you got electrophile means something which love electrons, and nucleophile means which love something which loves positive charge. So here is electron-rich triple bond, it loves positive charge. And here is a positive charge which loves electrons. So that means the hydrogen is going to add a cross to the triple bond first. There's going to be an attack of the pi electrons here onto the hydrogen to form this carbon-hydrogen bond. So you have formed this carbon-hydrogen bond, and you're going to get a carbocation. This is very similar to what we saw in the case of addition of HCl to double bond, because the H plus reacted or added to the double bond, and you got a carbocation. And exactly the same way here, you got a carbocation as well. And the Cl minus then nucleophile attacks the C plus, and you get a chloro-substituted alkene. So this reaction is parallel to the reaction we saw in the case of alkene. If this was CH3, CH double bond CH, CH3, you will get the addition of HCl, and you will get a carbocation with a single bond, and then the chloride will attach to that carbon over there. So it's very similar in nature to the reaction we saw in the case of alkenes. What if, so here we are talking about only one equivalent of HCl. That means there's only one equivalent of HCl present, and that HCl is reacting with a carbon-carbon triple bond to give you a carbon-carbon double bond. And you will get this compound in Z stereochemistry. Now, I'm going to ask you a question. Z stereochemistry, is that cis or trans? Again, I want answers in the chat box if you can write it. So my question is the Z stereoisomer cis or trans? We talked about E and Z when we talked about alkenes. So the question here is that this Z stereoisomer that is formed after addition of one equivalent of HCl, is this Z isomer? I'm telling you it is Z stereoisomer. So the question is this a cis alkene or a trans alkene? Is it possible to tell?
Ya,
Maybe I can draw
silakan. Yes.
Yeah.
Ya, silakan para mahasiswa kalau yang Z. Oh, yeah.
Okay,
There are
so
some
everybody is saying
answers.
Z is a cis. Let's see. This is Z Cl here, is CH3 here. Yeah, I'm just going to draw it for you. Yeah, and you have a CH3 here and a hydrogen over here, right? So what we said was when two priority groups are on the same side, then we call that a Z stereoisomer. So the two priority groups are, so there's CH3, sorry, here, there's Cl here. So the two priority groups are Cl is one priority group, and the other priority group is not hydrogen, but it is a CH3, which is a carbon. So the two priority groups are on the same side, and we call that a Z stereoisomer. So it's a bit like a cis because the two groups are on the same side. So that's why it's cis, but sometimes it's confusing. And if it's confusing, it is better to call it a E or a Z stereoisomer rather than a cis or trans stereoisomer. But here is a bit easier because the two groups are on the same side rather than away from each other. So that's Z, okay? All right, what if we use in this reaction excess HCl? So the first step in this reaction was we used one equivalent of HCl, and we got addition to the triple bond to give us a double bond compound. And then we used excess HCl. What will happen? So the first step, it will be the same. You'll get the same compound we got here because it's just one equivalent of HCl adding up. And this molecule is symmetrical. The two carbons are very similar. So it doesn't matter whether the hydrogen attacks here or there, you get the same compound. And then if you add the second HCl, is this the correct structure? Now I want you to think about the alkene chemistry we have done, and we learned a rule in that chemistry that when you add something to a double bond, you get one product forming. First of all, my question is this structure correct? Is this structure correct? why can't we get the second structure, which is possible here? So if we say the other possible structure is CH3, say we get Cl over here, and we put hydrogen over here, and then we can put CH over here, and we can put Cl over there, and we can say this is CH3. We can put CH3 over here. So this is the other structure possible. So the question I'm asking is this the correct answer which I have circled? And if it's the correct answer, why is it the correct answer? And somebody is very clever and they have given me an answer already. They say it's correct, and it's the Markovnikovs rule. Thank you very much. I'm glad somebody is very alert. So the HCl is adding to this double bond according to the Markovnikovs rule. The Markovnikovs rule said the hydrogen from the HCl is going to attach onto the carbon which has the highest number of hydrogens. So if you look at this carbon here, there is no hydrogen present on this carbon, while this carbon here has one hydrogen present. So this carbon has more hydrogen. So
udah mau diar gue belajar ginian. Lupa.
Sorry, is that a question?
I'm sorry, it's not, Professor.
Not a question. Okay.
Yeah.
So the hydrogen from the HCl will add to the CH to become a CH2, and the chloride will add to that carbon to give you the dichloro compound. So this is the correct answer. And the answer is because of the Markovnikovs rule, that the addition of the electrophile to the double bond gives you the compound where hydrogen is attached to the carbon
Kok cepet amat ya?
has the highest number of hydrogens on it. Okay, so this is Markovnikovs rule. But the point I want to convey here is that when you're looking at electrophilic addition of hydrogen halide to alkenes, you can get addition of two equivalents, not just one, because one equivalent gives you the carbon-carbon double bond compound, and the second addition gives you the compound which has Markovnikovs rule followed in the formation of that compound, and that's the product you get. Okay, let's move on. And also the thing to remember is when you have two substituents present on the same carbon, this is called a gem regioisomer. Gem means the two groups are attached to the same carbon, so it's gem regioisomer. Okay. All right, let's look at more examples here. So now we got two examples here. One is where you have this alkyne, which is a 2-pentyne, and we treat it with excess HCl. So we don't worry about adding one equivalent, we are adding excess. So the question is that there are two products possible in this reaction because the triple bond is not symmetrical. So one product you can get if you add H plus onto this compound, you could get a CH2. So one of the possible product is you got CH2, CH3 over here, and then you got carbon. You can have a double bond over here, and you can have your CH3 over here. So one product possible is you put hydrogen on that carbon, and you put Cl on that carbon over there. That's one possibility. The other possibility also is that you could put hydrogen on that terminal bond. So you can put hydrogen here, and you could put CH3 over here, and then you have your Cl present at this position like that. and then you have your CH2 and CH3 on this side, CH2 and CH3. So that's the second possibility, because the molecule is not symmetrical. So that's why you can have hydrogen adding here and chloride adding there, or you can have hydrogen adding here and chloride adding there. And these both compounds are possible. Once these compounds are formed, and then when you add a second equivalent of HCl, the Markovnikovs rule still applies. And if you apply Markovnikovs rule to that, you will say hydrogen will go here and the chlorine will go here. And that will give you this compound. And if you apply Markovnikovs rule here, then you will say hydrogen will go here and Cl will go to that carbon. And that will give you this compound here, which is again a dichlorinated compound. Again, a gem compound where you have two groups present on the same carbon. And you will probably get a mixture of these two compounds forming in this reaction, because it's very difficult to stop or favor one reaction over the other in this case, and you will get two possible products forming in this reaction. But when your double bond is symmetrical, like you got CH2, CH3 on this side, and a CH2, CH3 on this side, this is what we call a symmetrical internal alkyne. So this word internal means that the alkyne is not present at the end. So if the compound has this structure where you got a R, a C, and a triple bond CH, we call that a terminal acetylene, because, or terminal alkyne, because it's sitting at the end of the molecule. But if it's present inside the molecule, inside the chain, we call that a internal alkyne. And it's symmetrical here because the two groups are identical. So in that case, if you add HBr excess, you will only get one product. You can write the product like this, or you can write the product in a different manner, but they will be exactly the same compound. So if you can go CH2, CH2, sorry, 3 carbon, and then I wanted to put a double bond. Sorry, I'm just going to rub it off and start again. So you can actually have another product where you put CH2. Say you put the bromine over here. Instead of that carbon, you can put bromine over there. And you can have a CH2. But it'll be exactly the same compound as drawn at the bottom because, oops, because this is a CH3, and this side will have just CH2 3 times Br. So CH2, CH2, and CH3. So it got 3 carbons on the right-hand side and 2 carbons on the left-hand side. So there is only 2 carbons on the left-hand side, CH3, CH2. So there are 2 carbons here and 3 on this side. This structure has 3 carbons on the left-hand side and 2 carbons on the right-hand side. So it's the same molecule, whether you add H here or H here, it doesn't matter because it's a symmetrical compound. It'll only give you one product. Okay. The initial addition of proton can occur with equal ease to either of the sp carbons, and the geminal regioisomer always results. Sorry, I just need to rub this off because it seems like it has written on top of the text. So if you look at this, you will see that what we are trying to say here is that when you got a non-symmetrical molecule like that, the initial addition of the proton can occur with equal ease on the 2 carbons which are triple bonded, or we call them sp carbons. And the geminal or gem regioisomer always is the result. So you'll get a carbon with the 2 chlorines attached on it. This is called a geminal or a gem carbon, and this is the same geminal product, but the position is different, but the product is always geminal. And that is because of the Markovnikovs rule we talked about. Let's talk a little bit about stereoselectivity now of alkyne addition reaction. So we always get trans addition of hydrohalides or HCl or Br to the carbon-carbon triple bond, because the intermediate here is a pi complex intermediate. This intermediate is a little bit similar to the addition of bromines to the double bond, where you got this brominium ion formed in the middle. So this one here is a pi complex. So it's not exactly like the bromonium ion we got when we added bromine to a double bond. This one is more like a pi complex of the HCl to the carbon-carbon triple bond. It's like a pi complex. The pi electrons here formed a complex with H plus. And if that happens, then what's going to happen is the Cl minus is going to come and attack from the other side of the HCl, which is sitting at the top. So if that is sitting at the top, then Cl minus will come and attack from the bottom. So H is at the top, and then the Cl minus will attack from the bottom or from further away or across. And that what leads to this product here, which we call as a Z product. And Z product is the major product. So the 2 priority groups are on the same side. That's why we call that Z. But in relation to the proton and HCl, the Cl minus is always away from the HCl because of this intermediate species that is formed. So this is different from the one you get with alkenes. So with the alkenes, we get clearly demarcated bromonium species. You get Br and you get a plus charge here. In the case of alkenes, that's what you get when you're doing the reaction. Say if I put some substituent here of the bromine with carbon-carbon double bond. But here you're just getting a pi complex. It's not really formation of that bromonium Br plus. This is more like a pi complex where the Cl minus can attack away from the HCl. That's why the H and Cl are cross or away from each other. And that is what is shown in this slide. And adding excess Cl halide anion increases the yield of the trans product. So what it's saying is one HCl is already formed a pi complex, and then the excess Cl minus will improve the yield of the trans addition product. So what he's saying is one HCl is already used up, but if you have Cl minus, that will increase the yield of the trans addition product. Okay, so that's easy. Now the question is, what is the regioselectivity of alkyne addition reaction? Does the Markovnikovs rule still applies to alkynes? We know that the Markovnikovs rule applies to alkenes, but does it apply to alkynes? So particularly the terminal alkyne we're talking about here, and the alkyne is present at the triple bond at the end. So the question, if the Markovnikovs rule is favored, Markovnikovs rule says that HBr, the H plus from the HBr is going to end up this carbon, and the bromide will come up on this carbon over here. This is according to the Markovnikovs rule. The hydrogen will add to the carbon which has the most number of hydrogen on it. So this hydrogen has the most number of hydrogen on it. So the H from the HBr will add to the CH to give you CH2. And the positive charge is the carbon. And then the Br minus can attack that C plus to give us this structure here. So the question arises is why is it this favored over that? So the other possibility is if the H plus attaches on the left-hand side. So the other possibility would have been where we have a CH3, CH2. So basically what we are doing is adding hydrogen across. So CH3, CH2, this is one position where hydrogen added here. We're adding hydrogen over there. So we're making it as CH. And we are forming a double bond CH plus. So this was the other possible scenario that was possible, right? If the H plus adds here, we get this intermediate. And if H plus adds over here, then we will get this intermediate. So there are two carbocations possible, that one and that one. And then the Br minus will add here to give you this product. And if the Br minus adds onto this carbocation, then you will get the alternative product, which is going to be a CH3, CH2. Sorry, the computer is very slow. CH2, you're going to get CH double bond CHCl. Or CHBr. So that will be your product in that reaction if the second carbocation was formed. So the question is, does the Markovnikovs rule still applies? Do we get only this product, or do we get a mixture of this and this forming in that reaction? If you look at the two carbocation, there's one carbocation here, one here, just drawn this way over here. This is what we call a secondary vanillic cation. We call that a primary vanillic cation. So what do we mean by this vinyl? So any group which has a CH2 double bond CH, this is called as a vinyl group. This is called as a vinyl group, VINYL, a vinyl group. Okay, this group is called as a vinyl group. That's why we're calling that a vinyl cation and vinyl cation. This one here is a secondary cation. It's secondary because one side got carbon and the other side got a carbon as well in this case. This one is what we call a primary vinyl cation because it has a hydrogen attached over here and a carbon-carbon double on the other side. I think you're just comparing it with the corresponding compound. If there was no double bond present, then we would call that as a primary carbocation. So what I'm saying is, let's assume that there's no double bond present. So you have a CH2 plus, and this is what we call a primary carbocation. On the other hand, if you draw that as a without the double bond, you will have CH2, CH3, CH2, and then you have CH, and then you have CH2 or CH3 if we take the double bond away and put a positive charge here. We call that a secondary carbocation. This is a primary carbocation. The same way, this is called as a secondary vinyl cation. This is primary vinyl cation. And just like the one without the double bond, the secondary cation is more stable than the primary vinyl cation. That is again to do with the resonance stabilization. and also the stability of the carbon-carbon double bond cation. And you can see that the secondary one is more stable than the primary one. And if this is more stable, then this is the product that is you're going to get in that reaction. So the Markovnikovs rule still applies to the terminal alkynes in the case of carbon-carbon triple bond. Okay, the second hydrohalide addition affords a geminal dihalide. So the question is, why do we get a geminal dihalide like that? The carbon with the two bromines on the same carbon. And that is again mechanistically is shown here. You get the first addition in this case, the bromine shares electrons with C+, and that can help with the second addition. So when you're adding, you got the alkene as the first product that is formed when one HBr adds to carbon-carbon triple bond. And when the hydrogen attaches, according to the Markovnikovs rule, electrophile is over H+. So when H+ adds to the CH2+, you get a positive charge onto that carbon over here. And this positive charge is shared or stabilized by the bromine, which can share electrons with C+ over here. And then the second addition that is going to happen at the same carbon where the bromine is. So that's another reason why we get always a geminal dihalide, because if you add the first H+ onto that, you're going to get positive charge onto that carbon. So the intermediate for that will be a CH3. That's the structure that is drawn there, CH3, CH2, and you have your carbon with the positive charge over here, and then you have your bromine over here, and then you have your CH2, sorry, single bond. Just need to get the rubber. A single bond. I just make this bit smaller. It looks a bit unusual. So you get CH. So you get Br here, and you get your CH3 over here because the hydrogen has added across to that CH2. So you got a positive charge on that carbon, and that positive charge is stabilized by the bromine there because the bromine can share its electrons with a carbon positive charge. So that means this is the carbocation that is favored, and the bromine will then add here to give you the geminal dihalide. So that's why you get the geminal addition in the case of the halogen, second halogen adding to the double bond. Okay. So let's just talk a little bit about relative stabilities of the carbocation, because seems like the stability of the carbocation plays an important role in determining which product is going to predominate, is going to be the predominant product in a given reaction. So the relative stability of the carbocation is very, very important. We learned already in the case of alkenes, a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, and the methyl carbocation is the least stable of the all. But what about the carbocations with double bond? Where do they fit in according to this scheme? So according to this scheme, the tertiary is the most stable, followed by secondary, and then a secondary vinyl carbocation is more stable than primary carbocation, which is more stable than a primary vinyl cation, and then the methyl is the least stable. So the double bond ones fit in somewhere between the, one of them fits between the secondary and primary carbocation, and the other one between the primary and the methyl carbocation. So that means if a reaction is giving you a more stable carbocation, that means that's the product that will predominate in that reaction. So there is a sign here which says almost equal to, and this also says almost equal to. So not quite different between the primary and a secondary vinyl carbocation, only slight difference. So same here, primary vinyl cation and methyl cation are about the same. Just a bit of an explanation. A vinyl carbocation is formed in the first step of the alkyne addition reaction. When you do an addition of HCl or hydrogen halides to the alkyne, you get carbocations forming like this. They are the vinyl carbocation that are formed, and they are carbons which contain an sp carbon, sp hybridization, whereas the alkyl cations are sp2 is formed in the first step of alkene addition reaction. So the difference between addition of hydrogen halides to alkynes and alkenes is that in case of alkynes, the intermediate cation is a vinyl cation in the first step, whereas in alkenes, the first intermediate that is formed is the alkyl cation. So that's the fundamental difference between the two. And this is an example of an sp carbocation, and it has a higher or a high S character cation, and it interacts with the positive nucleus. While in the case of an sp2 carbocation that has less S character and is a more stable carbocation. This has high S character. And because it's an sp carbocation, because it comes from the triple bond has sp hybridization. So the carbocation has sp hybridization or sp carbocation. And in the case of the tertiary carbocation, comes from sp2 carbon. That's why the cation is sp2. And this has less S character, and that's why it's more stable. So S character is S. If you got S orbital, that means the electron is very positive. Oh, sorry, the center of the nucleus is very close to the outer electron. So that means the positive charge in the S character interferes with the positive charge on the carbon over here. So you got S character on that atom, and you got a positive charge. So it's like two positive charges close to each other. That's why this is less stable, while sp2 carbon is much more stable than, say, for example, a secondary vinyl carbocation. This is the reaction we looked at so far, is the addition of hydrogen halides onto the carbon-carbon triple bond. So the next question is, what about chlorines and bromines? Can chlorines and bromine add to alkynes? The answer is yes. And do they follow the reaction in the same way as the HCl? And the answer is also yes. So you can get one equivalent addition to the chlorine first, and then you can add a second equivalent of chlorine as well, because the first equivalent of chlorine converts the carbon-carbon triple bond to a carbon-carbon double bond, and addition of second equivalent of chlorine converts that bond to a single bond. And in this case, you get a tetrachloro compound forming. And you can see that the product, both carbons here, have two chlorines each attached to it. That means two equivalents of chlorine have added. And the same thing applies to bromine. if you do a bromine addition on a carbon-carbon triple bond, the first product will be bromine gone on one side, bromine gone on the other side, and then you will have second equivalent of bromine adding to give you that product. But also note that the two chlorines and the two bromines, they are away from each other. They are across from each other, because the addition here is again a trans addition where the second bromine is adding away from the first bromine in this reaction. Although this is called as a Z isomer, but this is a trans addition reaction. Okay, so what is happening in that reaction? Can we sort of think about what could be the detail here, or what could be happening? It's exactly the same as what we saw in the case of the carbon-carbon triple bond addition to HCl. But here you can imagine that you can get something like a Br species forming again in this case, and then you're gonna get the attack of the second bromine minus coming in and attacking that double bond. So it can attack over here, and this bond breaks, and you will get this trans addition of the double bond. While the second bromine addition also happens in the same way like we learned before. I'm just going to draw this structure slightly differently. So you can have a bromine up here, and then you can have a CH3 over here, and then you can imagine that you're going to form a C hydrogen and bromine over here, and you're going to have a bromonium ion formed just like before we learned in the alkene chemistry. You're going to get plus over here at that position, and then the second bromine minus will come and attack this carbon or the other carbon to give you the corresponding tetrabromo compound. So the chemistry is very similar. Let me just turn the light on, just 1 second. So the addition of the bromine is very similar to the addition of hydrogen halide. Instead of H plus adding first to give you the vinyl carbocation, you get the intermediate bromonium species, and then you get the attack of the second carbon, or the second, sorry, Br minus onto that to open up to give you the alkene product. And the alkene product then undergo the reaction second time around in exactly the same manner as we saw in the case of alkenes to give you the tetrabromo compound. So the fundamental difference between the addition of hydrogen halide double bond and the triple bonds is that you can get the reaction happening twice. And when the reaction happens twice, you get a geminal substitution product where the two chlorines or bromines are attached to the same carbon. When you look at the reaction of halogens, the halogens will add initially to the carbon-carbon triple bond to give you di-substituted double bond. And then a second addition happens, which then give you a tetra chloro or tetra bromo product in this reaction. Okay. All right, next reaction we're going to look at is addition of water to alkynes. So that's an interesting reaction. We learned about the reaction with HCl, HBr, HI, bromine, chlorine. What about water? Can we have two equivalents of water adding to alkynes? The answer is no. You only get one equivalent of addition of water to the alkynes. And what happens is when you add water to the alkyne, remember Markovnikovs rule, water is simply hydrogen OH. And according to the Markovnikovs rule, the hydrogen will go on the carbon, which has the highest number of hydrogen on it. So this CH here has higher number of hydrogen on this carbon. So that means this hydrogen will attach to that CH and the OH will attach to that carbon. So the first product you get in this reaction is this compound here, which is a carbon-carbon double bond, and it has a hydroxyl group attached to it. And we call these types of compounds as enols. There's ene for the double bond, and ol is for alcohol. So this compound here is an enol. And if you remember the aldehydes and ketones chemistry, we talked about keto-enol tautomerism. We talked about the ketones can exist in enol form, where you take away one of the hydrogens from the CH3, put it here, and then that double bond shifts to the oxygen to give you what we call an enol. And we also learned that the enols can be formed from ketones in the presence of acid or in the presence of base. And in most cases, the compound exists as ketone form. So we learned when we were talking about ketones and enol is that when you have, say, for example, a very common ketone, which we call acetone, is CH3CO, CH3, this exists in the keto form. This exists in the keto form. Majority of it. Less than 1% exists in the enol form. Unless there is some force stabilizing the enol form, typically the keto form is the most predominant form. So this addition of water to the carbon-carbon triple bond gives us an enol. And enol tautomerizes to what we call ketone, okay? And ketone form is the most predominant form. So that means starting with an acetylene, you can get a ketone compound by simply adding water. But this addition of water doesn't happen happily. You need to add a catalyst, a mercury salt in the reaction to make it go faster, to make it go to completion. And there's a reason for that, why mercuric compounds help in this reaction. So if you look at some more examples here, so this was an example where the acetylene is a terminal acetylene. Terminal means present at the end of the molecule. This is terminal. What if we have a symmetrical and an unsymmetrical alkyne? If it's a symmetrical alkyne, by symmetrical alkyne we mean there is a CH2, CH3 on this side, there's CH2, CH3 on this side. That means identical substituent, symmetrical alkyne. It's internal because the carbon-carbon triple bond is present on the inside of the molecule. And if you add water to the molecule, you initially gonna get the formation of the enol, and the enol then gonna tautomerize to give you the ketone. So the enol you will get will be a CH3, CH2, and a carbon with an OH, and you'll get a double bond, and you will get a CH2, CH2, and a CH3. So that's the enol you will get. And if you tautomerize it, you will get this ketone compound. If the alkyne is an internal alkyne, if it's present inside the molecule, inside the carbon chain, then you will get two possible products where hydrogen has added across here and the OH has added across here, or where hydrogen has added across here and the oxygen has added across here. So there are two possible enols in this product because it's not a symmetrical compound. So you could get CH3 where the OH adds to this carbon over here like that, and you get a double bond, and you get CH2 carbon-carbon double bond, and then you get enol, hydrogen goes there, you get CH, and then you have your CH2, CH3 attached to it. So that's one product you can get in this reaction. The second product you can get in this reaction is CH3 carbon, hydrogen is adding across here, so you get CH, then you get a double bond COH, and then you have your CH2 CH3 over here. So then this becomes your second enol, and then these tautomerize to give you the corresponding ketone compound. The equilibrium lies towards the ketone and less towards the enol. So this is an excellent method of synthesizing ketones. If you want to make ketones in the lab, you start with an alkyne and you add water to it in the presence of sulfuric acid and some mercuric salt, and you will get a ketone forming in that reaction. So how does it work? What's the mechanism? We're looking at reaction of this acetylene reaction with water in the presence of sulfuric acid and mercuric sulfate. You get this enol product following the Markovnikovs rule. Hydrogen adds here, hydroxyl adds there. This is what we call an enol. Enol tautomerizes to ketone. So what's the role of mercury in that reaction? Mercury is obviously a very poisonous compound, and we want to avoid the use of it as much as possible. And nowadays people try not to use mercuric compounds because of the environmental issues. So the mercury increases the rate of this reaction or rate of water addition to terminal alkyne. The way it does is that because this is electron rich, triple bond, mercury can form a bond with the carbons on the carbon-carbon triple bond. So it can form that bond. And that facilitates the reaction of water adding across to the carbon to give you the OH formation over there. And then the mercuric enol that is formed then is from there, the mercury is eliminated to give you the corresponding enol, which then tautomerizes to the ketone. So mercury basically helps with the rate of the reaction because mercury can form a complex with a triple bond, and then OH minus or the hydroxyl oxygen lone pair from water can attack the carbon, giving you the hydroxyl compound. Okay, so there's a reason why mercury works so well, but obviously we want to avoid the use of mercury because it's not a very good environmentally friendly chemical. Just to remind you about tautomerization, keto-enol chemistry, we learned that already in the carbonyl compound chemistry when we were learning that the ketones can form enol tautomerization or tautomer. This process is called as tautomerization. And in majority of the cases, the compound exists as a ketone. But small fraction of enol will also be present. And in some cases, we learned earlier on, if the enol is stabilized, then the molecule will exist as a enol form. And the example of that we looked at, just to remind you, was a 2,5-diketone. So if we have a ketone like this, which is like a 2, you call that 1, 2, 3, 4, sorry, 2,4-diketone, they exist, or they like to exist in an enol form. So you can put a double bond over here, and then you can have an oxygen double bond present in here. And then what happens is this hydroxyl, or the enol, forms a hydrogen bond with the second oxygen like this. Sorry, just a dotted bond here to form an enol, because this enol is stabilized by the carbonyl, forming a hydrogen bond. So here the equilibrium will lie towards this side and less towards that side, because this is stabilized by hydrogen bonding. And keto-enol tautomers can be formed by acid catalyst or a base catalyst. So if you have a ketone, you can protonate that ketone, and then that becomes your enol structure. So that means the first step here, which is not shown, will be R, hydrogen, hydrogen, and then you have your C double bond O. In the presence of acid, this will get protonated to put you a positive charge over here. And then you have your, R group here. And then simply this just comes around, and then this goes over here to give you that enol structure. And the acid is regenerated in the reactions. It's like a catalyst. Same with the base. With the base, you can remove one of the protons from here, and this pair of electrons move here. This moves over here to give you the enol, and the hydroxide is regenerated in the reaction. So it's not used up. That's why it's a catalyzed reaction, So the keto-enol tautomerism can be catalyzed either by acid or by base. And this is an important reaction. And just to show you how do you draw tautomers, you recognize the protons alpha to the carbonyl, and then protonate oxygen and deprotonate carbon for the enol species. Sounds very complicated, but it's very easy. What they're saying to do is this is the keto form, and you want to write an enol form of this. So what they're saying is you basically remove one of the protons, and this proton can be removed, or one of these can be removed. It doesn't matter which one. If that is removed, you form a double bond, and you make that oxygen and alcohol. And since there are two possibilities here, you can have the second product possible as well as an enol. So the key requirement for the existence of keto-enol tautomerism is the carbon next to the carbonyl must have hydrogen present on it. If it has hydrogen present on it, only then it can form the enol species. If there's no hydrogen present, then it cannot form the enol species. And the example is here. So no proton, no enol tautomer. So if you have this molecule here, for example, the benzophenone compound, there's no hydrogen present on this carbon. There's no hydrogen present. And there's no hydrogen present on this carbon. So that means this molecule here cannot form an enol. It can only exist in the keto form. Okay, now let's quickly look at the addition of hydrogen. We saw the addition of hydrogen in the case of alkenes as well. And we found that hydrogen adds to the alkenes to give us the alkanes. The hydrogen adds across to the double bond. And hydrogenation, we call that hydrogenation, and it's typically carried out by hydrogen gas and a catalyst. And the catalyst here is palladium. But since this molecule, alkynes have triple bond, it can react twice with hydrogen. The first step is the formation of alkene. You add one hydrogen here, and you add one hydrogen here, and you will get alkene. And also, the second molecule of hydrogen can add as well. And then if you add hydrogen here and a hydrogen here, you will get the corresponding alkane compound. So that means the triple bond can react via the double bond to give you a single bond. And this reaction sometimes is very difficult to control. If you're using hydrogen, palladium, and charcoal, you can see this reagent is same as the reagent for reducing the double bond. So if you do the reaction, you will find that you will just get it reduced all the way to alkane. What if we want to stop the reaction here? What if we want to get alkenes as the product in the reaction? So in order to do that, we use a catalyst which we called a poisoned catalyst, developed by this person here called Lindlar. And this catalyst is also called as a Lindlar's catalyst. And basically, it's a poisoned palladium catalyst. So that means the reaction with hydrogen now will only give the double bond compound. And also, it is important to note that the reaction between triple bond and hydrogen always give you a syn addition. That means two hydrogens will be present in cis relationship. They'll be always present on the same side of each other. We saw earlier that when we have HCl, we got a trans addition. When we had bromine, chlorine, we got trans addition. But when we have hydrogen, you always get cis or syn addition. That means two hydrogens come from the same side of the molecule. And if you use poisoned catalyst, then you can stop the reaction at the carbon-carbon double bond stage. So what is Lindlar catalyst? The component of the Lindlar catalyst is palladium metal because we need the metal, but it also has a poison called calcium carbonate, which reduces the reactivity of the palladium catalyst. And the origin of cis chemistry is that exactly the same like we saw in the case of alkenes, the hydrogen added from the same side to the double bond. And the same here, the hydrogen adds from the same side to the triple bond. First of all, hydrogen gets bound onto the palladium catalyst, and then there is breaking of hydrogen-hydrogen, and then hydrogen attacks that carbon-carbon triple bond as a radical, and then you get the formation of carbon-hydrogen bond from the same side. Delivery of the hydrogen atom to one side of the solid phase catalyst. That's why we always get. The last thing we want to look at now in case of alkynes is what is the acidity of the carbon-carbon triple bond. So if we have a R, C, triple bond, CH. So the question is, can we remove this hydrogen here? Can we somehow generate a carbon minus and H plus species, because the acid is able to give away a H plus. So how acidic is that hydrogen? How easy it is to take that pair of electrons away in terms of reagent or a base. What is the acidity of the acetylene? If you look at sp carbon versus sp2 carbon and versus sp3 carbon, that means we're looking at sp carbon over here, and an sp2 carbon will be when you have a carbon-carbon double bond, and you're looking at this hydrogen here. This is your sp2 carbon, and sp3 is when you have just a single bonds present in a molecule. Then how easy it is to remove the hydrogen here. The carbon, which is sp, is the most electronegative carbon. So that means this is going to be the most acidic, and sp2 is less electronegative and sp3 is least electronegative. Just like compare HCl. Cl is more electronegative than hydrogen, and hydrogen can be removed as H+. Sp triple bond CH is the most electronegative carbon, and hydrogen can be removed easily here compared to sp3. Higher s character, sp orbital penetrates nucleus, lower s character, sp3 orbital penetrates nuclear to a less extent. So that means it's harder or less electronegative. Now, if we compare ethyne, alkyne, alkene, and alkane, the pK is a measure of the acidity of a compound. If pK is smaller, then the compound is more acidic. And if pK is very high, then the compound is least acidic. So out of alkyne, alkene, alkane, alkyne has the lowest pK value. And because of that, this is most acidic compared to these three. Alkyne is more acidic than alkene, than alkane. What about if we compare it with other things like water, ammonia, and hydrofluoric acid? If you compare it, so there is your alkyne, it has a pK value of 25. It's less acidic than water, and it's also very less acidic than hydrofluoric acid, because HCl, HBr, HF, we're talking about very strong acids here. While water, ammonia is a very weak acid, alkenes we know, and alkynes we know are the weakest. Sorry, alkanes are the weakest acids in these reactions. So that's just a comparison of electronegativities and electronegativities versus the acid strength of the molecule. Smaller pKa means strong acid, and larger pKa means a weak acid. So the implications of this then to acetylene chemistry is that we can remove that proton that is present on that carbon-carbon triple bond. And if we can remove that proton, you're going to need some sort of strong base. You're not going to be able to do it with a weak base. You're going to need a strong base. And if strong base can remove that proton, this becomes like a acetylide ion where carbon is minus. And that is very similar to a character in Grignard reagent. If you look at Grignard reagents, which we studied earlier on, say, for example, the methyl, magnesium, bromide or chloride, these are the Grignard reagents. We know that the minus carbon here is your nucleophile in the Grignard reagents. And same in acetylenes, if you remove that proton, you get a carbon negative acetylide. And that is a strong nucleophile and can react with lots of other reagents. So basically sodium amide, which is strong base, can remove that proton from the acetylene to give you an acetylide. So if this was sodium amide where you have Na plus as the counter ion, Na plus, So basically you will get Na plus with the salt here, with acetylene if you remove that proton. Okay, so you can get this acetylide ion. The hydroxide solution here may not work in this case because hydroxide is a weaker base, and the weaker base may not be able to remove that proton because the acetylide ion is a strong base while this is a weaker base. So this reaction is probably going to lie more towards the left-hand side rather than going to the right-hand side, because this OH minus is a weaker base while this one is a stronger base. So you're trying to generate a stronger base with a weaker base, and that's not going to work. You can generate a weaker base with a stronger base here, and the equilibrium will be towards the right. Okay, so you need a strong base to remove that proton from the alkyne, and once it's removed, then you can do the reactions with it. And I'm just going to show you one or two reactions on how this can be used. It can be used to form a carbon-carbon bond, just like a Grignard reaction is used to form carbon-carbon bonds. This acetylide ion can be used to form carbon-carbon bonds. So if you have an alkyl halide, you can attack that CH2 on the alkyl halide because bromine is more electronegative. So the negative charge is on bromine. CH2 is slightly positive. This carbon can attack, or this acetylide ion can attack that CH2 to give you this product over here, where you form a carbon-carbon bond between this carbon and the CH2 over here. And you can see that this reaction is very, very useful in extending the chain of a reaction. You started off with a 4 carbon and 3 carbon, and you got a 7 carbon product in that reaction. And you can imagine that you can further modify this compound by adding water to it. Then you can generate a ketone, or you can add hydrogen halide or bromine to this compound to generate other products. So acetylenes are very useful compound, and they can be used for the synthesis of quite a large number of compounds to give different products. So we can convert a terminal alkyne to a longer internal alkyne by addition of alkyl halide. So this was our terminal alkyne at the end. And now the product we get is an internal alkyne where the chain has become quite longer in that reaction. Okay, I think this is the final slide as far as I can remember. This type of question is what we call a retrosynthesis question. So the question is asked is that how you can convert this acetylene into this product. So that's the question, that how can you convert that alkyne into that product, CH2, CH2, OH. So you can start thinking backwards and think how I can get this compound from the starting alkyne compound that also has 2 carbons, that also has 2 carbons, but this has a OH group attached to it, and there was no OH group in the starting compound. So one way you can start thinking is that maybe this compound can come from an alkene. CH2, CH2OH can come from alkene. And then perhaps alkene can come from triple bond. So my question is that how would you get an alcohol like that from an alkene? Is there a simple way of converting that CH2OH from the alkyne or alkene itself. Okay, so it is possible, but first of all, to go from triple bond to a double bond, you can have Lindlar catalyst. We just learned that if you use poisoned catalyst, you can convert a triple bond to a double bond without going to single bond. So this first step can be carried out by what we call a Lindlar catalyst. We don't worry about this one because that we didn't cover in the lecture. So that's a different compound. But you can use the poison catalyst to generate that carbon-carbon double bond. So the question then is, how do we get this compound over here, a CH2OH, in this reaction? Or can we think of another way which might give a compound which looks something like 6-member ring? It might give a CH-OH and a CH3 over here. So that's the question. How do we go from here to there? Maybe let's just ask some people in the chat that how can you get that alcohol from the carbon-carbon double bond, CH-CH2. We have CH2-CH2, CH double bond CH2, and we want to get CH-OH-CH3. What should we do? Anybody, what should we do?
Ya, silakan untuk para mahasiswa, bagaimana cara mendapatkan alkohol yang digambar di bagian bawah begitu ya dari alkena. Menggunakan reaksi apa atau adisi apa?
What reagent we need? What do we need?
Ya, silakan bisa ditulis reagennya apa. Adisi alkena menjadi alkohol.
What have we added to the double bond? I think that'll give you an idea. If you look at the double bond and the product, what is the difference between the two? What have we added on one side and what have we added on the other side? That will give you an idea as to what is happening in that reaction. If you look at the product, we have added OH onto that double bond on this side, and we have added hydrogen on that side. So OH plus hydrogen is water. So we have added water onto that alkene to give us that product. And this product is following Markovnikovs rule, because Markovnikovs rule said that hydrogen will add to the carbon which has the highest number of hydrogens, so that's CH2. So the hydrogen will add here, and the hydroxyl will add to the second carbon. So that seems to follow the Markovnikovs rule, Markovnikovs product, to give you that product. So it's just addition of water to the double bond, and that addition happens with aqueous acid, and you'll get this Markovnikovs product. But this side here, if you look at this product also has a hydrogen added here and a hydroxyl added here. This is also an addition of water to that carbon-carbon double bond, but the product we got is what we call an anti-Markovnikovs product. Markovnikovs product is down here, but this one is anti-Markovnikov. Anti-Markovnikovs means that it does not follow the Markovnikovs rule. It does the opposite. The hydrogen goes to the carbon that has lesser number of hydrogen, and hydroxyl go to the other carbon. So hydrogen has gone to the carbon with lesser hydrogen compared to the CH2. So this is what we call an anti-Markovnikovs product. An anti-Markovnikovs product can be generated by this reagent here. I don't want you to worry too much about it, but it is possible to do this reaction with BH3 followed by treatment with base and hydrogen peroxide, and that gives you the anti-Markovnikovs product. All right, I think I'm gonna stop here and then leave some time for questions, because we finished off now the alkyne part already, and we learned that alkynes are in some ways similar to alkenes, but there are double reaction possible because of alkyne going to alkene and then alkenes doing the second reaction. But the reaction with water was quite interesting to the triple bond, because that gives us the formation of ketones. So if you have any questions, I'm happy to answer the questions.
Yeah. There's one question in the chat.
Okay, so the question is two questions. Nomenclature, which one is the correct name? 2-ethyl-1-butene, 3-methylene pentane, and 2-pentfluorine. So I need to go back to the slides. Just hang on a second. I just share my screen again, and I will go back to the nomenclature so I can try to explain it once we are over there. Nearly there. Okay, so we got nomenclature over here and here. So let me just go back to the chat and see. So one is 2-ethyl. Let's do the second one first. 2-pentene-4-ine and 3-pentene-1-ine. Have I got that structure here? Probably not. So what you're saying is, you're saying 2-pentene-4-ine. Let me just draw that. So it's 5 carbon. So let's just draw 5 carbons. You got carbon. I'm just going to draw carbons just for clarification's sake, rather than trying to draw hydrogens as well. So we got 5 carbons like that, right? So that's pentene. So it says 2-pentene. 2-pentene will be when the double bond is at the 2 positions. So it's 1, 2, 3, 4, and 5. So you're saying is 2-pentene-4-ine. So triple bond is over here. So that's the name corresponding to that structure, 2-pentene-4-ine. Or, so if I draw that again, so the question next, or the next part of the, so excuse the writing because I'm trying to draw it with the pad, which is difficult. So it's or 3-pentene and 1-ine. So 3-pentene will be, if I just take it there, 3, 4, 5. So we are saying it is 3-pentene. So pentene gets double bond, gets the first number, and 1-ine. No, 1-ine is not correct because you need to give it the lowest number to the alkene. So this is the correct name, while the other one you're suggesting is the wrong one. So this one here is the wrong name. The correct one is that one, 2-pentene-4-ine, which is that one. The first part is 2-ethyl-1-butene. So this is incorrect. So 2-ethyl-1-butene is when you got 4 carbon chain. And what you're saying is 2-ethyl-1-butene. So 1-butene will be the double bond that's preferred here. And then you're saying 2 is ethyl, so it's 1, 2, 3, 4. And then you have your ethyl group, which is CH2, CH3 over here. So that's the name, correct name. The other name you're saying is 3-methylene pentane. 3-methylene pentane. So pentane is 5 carbon. So if you call that 1, 2, 3, 4, 5. So you put double bond here. You won't call that 3-methylene pentane. You won't call that 3-methylene pentane. So that's incorrect. So the first name is correct. 2-ethyl 1-butene, which is that one. Okay, that answers that question. Okay, I have a question. The beginning of the slide that shows the reaction between 2 pentenes with HCl. Does the product give the same amount of product? Does not form major or minor product, because I still think maybe the product will be more inclined to dichloropentene because of the induction effect of the propyl group on the light hand. Okay, let's just have a look at that question. So the question is here. 1, 2, 3, 4. It's on this slide here. Okay. All right. So the question is that when you got the 2-pentyne and we use HCl and we are saying we're getting 2 products, does it form major and minor? Because I still think maybe the product will be more inclined to 2,2-dichloro because of the induction effect on the propyl on the left-hand side. So the question is, maybe this could be the major product, this could be the minor product. Let's just draw the intermediate. I think I drew it earlier. I don't know if they're still there. Let me just check and then see if, no, I think I rubbed them off. So the 2 possible ways that you add hydrogen across here first onto the triple bond, and you get a double bond formed first in that reaction where you put the Cl and a CH3, right? And if we draw the corresponding, say, carbocation to that, the carbocation for that will be just the positive charge here. So the carbocation will be simply carbon double bond with a positive charge and a hydrogen over here. And then you got a group attached over here. And then you have your CH3 is over here. That's one possible carbocation. And the other possible carbocation is where you can have your hydrogen added across here. And you have your CH3 over here. And then you have your double bond carbon with a positive charge. And you have your CH2, the propyl group over here, CH2, 1, 2, 3, 4, 5, CH2, CH3 over here. So these are the 2 possible carbocations. In one case, the carbocations are very similar in nature. You can see that they are like secondary carbocations. That's secondary carbocation. That's also secondary carbocation. This carbocation has ethyl group, and this carbocation has methyl group. There's not going to be a lot of difference between the stability or imparted by the methyl versus the ethyl group. So my feeling will be that it'll be still very similar amounts of the 2 products formed. But so you are arguing that there's a propyl 2-pentene because it product same, does it major more inclined because the induction effect of the propyl group on the left hand side. So the induction effect is a methyl group on that side and the ethyl group on that side. So there wouldn't be a lot of difference between the induction effect of the methyl versus ethyl. So I assume that you're still going to get pretty much very similar products in that reaction. Okay, next question.
Yeah, I think students, if you still have any questions to Professor Naresh, or maybe Prof. Asep, do you have something to say? Or we have Ibu Amelinda and then Pak Hayat.
You can ask me questions about University of New South Wales if you like.
Yeah, so aside from the lecture, you can also ask about UNSW in case you're wondering how maybe to apply for postgraduate study at UNSW or anything.
Yeah.
Yeah, because there are some Indonesian students also who did the research at the UNSW, right? I
Yes.
mean, yeah. All right.
Professor Sholihan and Vidya are two examples here.
Yeah, from the, for example, from the Gajah Mada University, when
Yes.
when they were doing the final project for the undergraduate
Yes,
study,
right.
yeah, they also did the research at the UNSW. So
Yes. So
yeah.
I had about 4 students so far from Gaza Mada.
All
They
right.
came to do their research in my lab. And one of them is now applying to do a master's degree at UNSW.
Oh, that's good.
Antari is her name.
Yeah. I know her.
And we had this very good experience for students to come to Australia, to UNSW, and experience the research labs we have, and also participate in some research projects which we are doing. Then you can write your thesis based on that project.
Yeah, so it's about it's for around 3 months or less than 6 months, I think.
Yeah, they can come for one term, which is 3 months.
Yeah.
Or they can come for 6 months, which is 2 terms. So it's up to the student how much how much time they can afford, and obviously how much expenses they can afford.
Yeah, so hopefully UPI or Universitas Pendidikan Indonesia can also send students, some of the students to UNSW, because absolutely you can experience different atmosphere, especially in terms of the research facilities.
Yeah, we are one of the big universities in Australia, and we have the top class facilities available anywhere in the world.
Yeah, I'm still amazed of the NMR facilities that the UNSW had. Like, you can,
have 7 NMR machines.
Yeah. Sometimes for most of the students here are facing difficulties when they have to use the NMR, because they have to send the sample to other institutions. So hopefully, I mean, by this program, like collaboration or collaboration, we can yeah, it can ease the research that are doing by the students. So
Yeah, it's good.
yeah, so anyone who still have questions for Professor Naresh, because it's the last lecture in
Hopefully when the borders will open, I will come to Bandung.
yes, you should. Is there anything? Okay, the hopefully by so for the total of 10 meetings, hopefully the students can get better understanding, especially in the topic of monofunctional compounds or polyfunctional compounds. And at the verse of at the beginning of the lecture, Professor Norris also gave us introduction into the drug discovery and development. And yeah, thank you so much, Professor Norris. It's been valuable for us to get lectures from you, and hopefully we can see each other in the next occasion. Yeah, if it's not face to face, hopefully we can still have another opportunity to see virtually.
Yes, yes, yes. If you're organizing a conference, I will be happy to.
Sure, yeah, yeah. In the next year, I think yeah, we still have like webinar, maybe if it's still online system, and hope to see you again sometime soon.
All right. All right. Thanks, Vidya. Thanks for inviting me to be the visiting professor, and thanks for organizing all the talks and sitting through the talks, listening to me for talking end to end. But I enjoyed interacting with the students, and I wish them all the best, and wish you also the staff very best as well. And
Thank you.
like you said, hopefully we'll see each other soon.
Yeah, thank you. And for students, maybe you have to prepare for the final exams. So,
Yes.
yeah, so the final exam maybe will be started in the next 2 weeks. So hopefully by the lectures from Professor Norris, you can still see all the lectures from the YouTube channel of our department. In case you miss something, you can always find the answer to our YouTube channel, because all these lectures are live streaming on our YouTube channel. So yeah, thank you once again, Professor Norris. And if the students have no more questions, I think we could end this session. And it's very sad, actually. Yeah,
Anyway,
I think I'm gonna miss all your lecture, Professor Norris.
don't worry. We'll be in touch anyway, so we can always communicate by mail or conference. Yeah. Okay, I will see you guys next time. All the best, everybody.
Yeah, so thank you once again, Professor Norris, on behalf of the Department of Chemistry Education. Yeah,
Thanks, Gabby.
especially
Bye.
the organic teaching staff. Thank you once again, Professor Norris. See you again. And stay safe and have a good health.
Yeah, everybody, same to everybody. Thank you. Bye.
Thank you, Prof.
Thank
Naresh.
you.
Bye. Thank you. Thank you.
So, terima kasih untuk para mahasiswa yang sudah bergabung begitu ya untuk perkuliahan visiting professor bersama Prof. Naresh. Jika ingin refresh kembali begitu ya, ada rekamannya di YouTube channel Departemen Pendidikan Kimia, bisa di searching di sana. Kemudian nanti juga akan ada sertifikat bagi peserta yang mengikuti at least 80% dari lecture yang diberikan oleh Profesor Naresh. So yeah, for all participants, there will be we will provide certificate for those of you who join at least 80% of the lectures from Professor Naresh, and we will send the e-certificate through the email that you provided to us. And thank you for all participants. Thank you also to organic teaching staff from Department of Chemistry Education, Ibu Gebi, Ibu Amel, kemudian tadi ada Pak Hayat, Pak Asep. Terima kasih telah membersamai saya. Gitu. Terima kasih. Mudah-mudahan dengan adanya visiting professor ini bisa menambah pengetahuan tidak hanya bagi mahasiswa, juga khususnya bagi saya begitu ya, mendapatkan banyak sekali ilmu dari Profesor Naresh. So thank you to all participants. See you again in the next lectures or in the next event held by Department of Chemistry Education. See you and have a good health. Have a good rest. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Mohon Bu Vidya, Bu Amel.
Mohon Ibu Gebi.
Turun Ibu, ya Ibu Gebi. Turun Bu Vidya.
Nuhun juga Ibu Amel, untuk link presensi ada di chat. Saya